So this in the last class we have seen that how Google with a randomized policy, whatever objective they had the objective that okay, minimum number of as many minim or I mean as many less number of guys to be hired as possible. That was their objective. Okay, and Google with a randomized policy, we have seen that okay, there is a sense, there is one intuitiveness that okay, Google might be able to achieve that. And our claim was that okay, if we are if Google is having a list consisting of this n number of cardinality of n, that means this n number of candidates to be interviewed, then if the list is randomized, then Google can end up hiring order of log n number of candidates. That was our claim. We haven't proved it. Okay, that is our claim. That okay, Google will be able to achieve this thing, right? Google or Facebook or Amazon, whoever is coming, Microsoft, right? So we cannot keep Microsoft away right now because this there is a term which is coming. This is Chat GPT. So this is coming into picture, and maybe Google is fearing that okay, their era might be ending with this, but time will tell who going to win. Anyway, so anyway, this is this whenever this randomization is in place, then obviously what is another thing it is in place is this probability. Okay, probability will be coming into picture, right? So this probability will be coming into picture, and what we got to do to understand this thing, that ultimately we're going to prove that in number of candidates, if I randomize, then we will be having order of log n number of candidates to be hired. Okay. So how can we prove this thing? For this, we need to have this probability. Little bit we'll be having a recap on this probabilistic aspect, and then we'll be going for this. So this elementary probability that you have got your idea in engineering, mathematics perhaps, and in 10th 12th standard right now I have seen the syllabus is containing probability, but in that maybe one thing which will be necessary heavily is this expectation of random variable that perhaps is missing in this 10th 12th standard mathematics, maybe, if I'm not absolutely sure. Anyway, we'll be covering this from the very basic to this expectation of x, then we'll be coming back to this analysis process. Okay, we'll be coming back to this hiring assistant problem. Okay, hello you guy, you, are you listening? You, yes, you, you. Stand up, are you listening? What am I teaching? Not teaching anything. What, what am I telling? Randomized algorithm. And then what I have said, few sentences. कल वाला क्लास नहीं किया? हाँ, नहीं आज वाला क्या बोला? कुछ नहीं. हाँ, इधर आ जाओ तुम, इधर बैठो. going into that probabilistic aspect, one thing we have to know that what is the definition of this randomized algorithm? Which algorithm we will be calling that this algorithm is a randomized algorithm? Okay, right. So here in our example of hiring assistant problem, right, what we have got an input that is list of candidates, that is n. Okay, n number of candidates we are having, right? So in say whenever we are sorting uh, some some numbers, whenever we are sorting some numbers, right? We are given one array or a list of numbers and we are sorting these numbers. Okay. And at that time, what is the input? Input is, can you tell me what is the input, you guys? No. Who is having the laptop? Say we have to sort this L list which is having numbers. Okay. What could be the input of the algorithm? Oh, we have to sort some numbers. I am forgetting about this hiring assistant problem. This is a general sorting problem. Then what is the input to the problem? Input. You are giving some input to the sorting process. What is that? What you are doing with laptop? Reading something? Huh? Okay. So can you tell me what is the input? Huh? No, no. This any numbers you are putting there in the list. So the input is the n numbers. N numbers is the input. Okay. And you see what we are doing, we are taking this input and then we are transforming it into a sorted array. We are taking one array which is not sorted, say, and then we are having this output. And along this way, say if you are thinking about any comparison based sort so far, whatever you have got, then along the way you are comparing numbers and ultimately you are getting this. Okay, right. But the thing is that here, after getting the input, what we are doing in this hiring assistant problem, we are randomizing that list. We are randomizing that list, okay, and we are getting some that number in another configuration, say in prime. I am telling that, okay, the same numbers but in different order, okay, and then we are taking the help of this any classical algorithm, okay, and then we are getting the output, okay. So previously we had a sorting algorithm, but that sorting algorithm was directly given into the problem, okay. But here what we have got a list of candidates or numbers or whatever, and then we are applying one randomizer to it, one randomizer, and then we are channelizing that input, that modified input into the algorithm. Okay. So what we are doing essentially, little bit different viewpoint we are having. Previously, no randomizer was involved. Now, to improve the algorithm, so why we are using the randomizer? To improve the algorithm, the whatever objective we are having. Okay. So Google's objective is to hire as less number of candidates as possible. Okay. So to have this, they are randomizing. So to improve the improve the efficiency of the algorithm, what we are doing, we are using one randomizer. Okay, along the way, along with the input. Now, whenever we will be taking along with the input any of this, I mean, a randomizer is also involved to improve the efficiency, or maybe we can test also with this randomizer. So when randomizer will be involved along with the input, then that algorithm will be calling a randomized algorithm. Okay, so that is the basic difference. When we will be calling one algorithm randomized, or when we will be calling an algorithm not randomized. Okay, so there is a sorting algorithm which is the quick sort. Whenever we will be taking the quick sort, okay, so there is a deterministic algorithm where no randomizer is involved. That means either the first element or last element or the middle element will be taken as the pivot, and then based on that pivot we'll be comparing each of the elements with that pivot, and then we will be making two lists. One pivot will be here, and which will be less equal to this will be this side, greater than this will be this side. Okay, now whenever we are fixing this pivot, first element or last element, then we will be in trouble in quicksort. Maybe the time complexity may be more. Okay, instead of fixing this pivot, now to improve the efficiency, say what I am doing is whenever a list is given, right, or a sublist is given, so this sublist will be recursed separately, and this sublist will be recursed separately after that. So whenever a list or sublist is given, then what I'll be doing, I'll be randomly choosing one element as the pivot. So I may choose this element, or I may choose randomly this element. Whatever uh, element I am choosing randomly, that will be becoming the pivot. So now what we are doing, so previously we are not taking the help of randomizer, and here along the input we are taking the help of the randomizer, and maybe that process can increase the efficiency of the algorithm. Okay, so then this we'll be calling this quicksort as the randomized quicksort. Okay, so this is the difference between this randomized one and not randomized one. So along with the input, a randomizer will be there. That's we'll be calling randomized algorithm. I guess you have got this point. Okay. Now this probability, little bit probability we'll be having here in this course right now to proceed further. So the first thing is that we need to understand this sample space. Okay. We understand this sample space, but always it is better to have a recap on this. Okay. So we define probability in terms of a sample space which we denote by capital S, okay, and which is a set of elements, which is a set whose elements are called elementary events. Okay. Now let us take one example. Uh, so elementary event, you can think of it as a possible outcome of that experiment. Okay. Say we are flipping one coin, or we are flipping a coin. Then whenever we are flipping a coin, what will be the outcome of this experiment? It could come up as head, or it could come up as tail. Okay. One coin whenever I am flipping, is there any other outcome possible? So no outcome like Sholay that we are excluding. Okay. Have you seen Sholay movie? Everybody? So this H and T, okay. So this head is one outcome. Wait. Head is one outcome and tail is one outcome. Okay. So these are two outcomes possible of this experiment whenever I am tossing a coin. Okay. So this is also the sample space. Okay. So this outcome is called one elementary event. Elementary event. Okay. And this is also one elementary event. Okay. So the sample space consisting of elementary events, and elementary events are nothing but the outcome of this experiment. Okay. Right. Now say whenever we are flipping two coins simultaneously. Two coins simultaneously. Right. So in that case, what will be the outcome? So both the coins might be landing as head. Okay. So then maybe HT, one is head, the first one is head, second one is tail. Then first one is tail, second one is head. Then first one is tail, then second one is tail. Okay. No other outcomes possible whenever I am flipping two coins simultaneously. Okay. Or I am flipping one coin after the other, and I am seeing that two coins one after the another as a big experiment. Okay. So this is the sample space in that case. So this is the sample space whenever we are flipping two coins. Okay. Now, what will be the sample space? Sample space whenever we are flipping three coins simultaneously. So H and some other. Maybe we can write in terms of that. Say head is 0 and tail is 1. So in that case, it is easier for us to write. I can write 0 means tail. Okay. Then 0 and 0 1 0. Okay. 0 1 1 and all these things coming up. Right. So this is the sample space whenever I am flipping three coins simultaneously. Right. So now we have got we we have a recap on this sample space. This much you know. Okay. What is called sample space, but again, as this will be coming heavily, even if we know this thing, whenever this coin flip experiment comes along the way, then what happens is that we readily understand what is the sample space. But when a new problem is coming to us, we fumble. Okay, we fumble. Even if I fumble. Okay. So I think understanding this sample space is a big thing in probability theory. Because once we are understanding this sample space, then everything is done. Okay. So whenever one experiment, first of all, we have to understand what the experiment is. Where lies the randomness? Where lies the uncertainty? Okay. And then we have to figure out what is the sample space. Okay. So then we can have our life easier, right? Okay. We can move forward. And the next thing which will be very essential to know is this event. Okay. This is very important for probability to have some meaningful statement. Okay. So an event is a subset of the sample space S. For example, in the experiment of two coins we are flipping, then the event of getting one head and one tail. Okay. So we had the sample space, this HH, HT, TH, and TT. Okay. Now I'm looking for the event that getting one head and one tail. Okay. So which are the elementary events? So this is a subset of the sample space. Once we are having the sample space ready, we can have the meaningful event that can be customized by us. That can be customized, that can be, I mean, the objective, based on the objective, we can look for some of the events. Okay. Some of the events will be defined as a set of the sample space. Okay. A subset of the sample space. Okay. Now, one such event I am looking for is getting one head and one tail. Now we have to look to this whether this guy is satisfying that condition. One head and one tail. So this is HH, it is not satisfying. Now I am looking to this sample space HT. Okay. This elementary event satisfying this one head, one tail condition? Yes. So HT will be in that subset. Then I am looking to another elementary event, TH. Is it satisfying? Is it satisfying? Yes. Hmm. Yes. Okay. And then TT. Is it satisfying one head, one tail? No, because both are TT. Okay. So this is the event we are looking for. Say we are naming it as A. So now if I look back little, if I pause here and if I think that what's happening out here, this is very fundamental. We have to know what is this sample space, all the elementary events, and some of the elementary events will be defining the event space. Okay, that means some of the elementary events we can have in a subset which will be defining that event. Okay, this is very important, and this definition will not be violated whatever experiment you are having in probability space. Okay, right, this is absolutely fixed and final, right? So this sample space, understanding of this sample space and understanding of this event, the event comprising of this subset of these elementary events. Hello? আচ্ছা ঠিক আছে ঠিক আছে Okay, so this now another thing is that okay, we have to know this when two events are mutually exclusive. Okay, when this A intersection this B is becoming null. Okay, so at that time two events are called mutually exclusive. Say whenever we are throwing a die, okay, six-sided die, the A is comprising of the odd numbers, and then B comprising of the even numbers. Okay. So this might be comprising of which outcome? Can you tell me? 1, 1, 3, 5, and this is 2, 4, 6. What is the sample space? Can you tell me? 1, 2, 3, 4, 5, and 6, I guess. Okay. And then you see the A is the odd numbers, which is 1, 3, 5. Okay. And this is B is the even number, which is 2, 4, 6. And there is no common element between these. So A intersection B definitely will be null. Okay. So these two events are mutually exclusive, right? And by definition, so this is one elementary event. Say maybe we can name it as say E1, maybe we can name it as E2, okay. Maybe we can name it as E3, maybe we can name it as E4. And now these elementary events, so by definition, these are mutually exclusive. So E1 will not be having any common element with E2. Not will be having any common element with E3 and E4 and so on. Likewise E2, likewise E3, likewise E4 case. Okay. So this is the elementary events. That means the outcome of the experiments. Each individual outcome. If I am taking this any pair of these two events, elementary events, they are mutually exclusive because there should not be any common element. If one is happening, the other one will not be happening. Okay. Right? Hmm? Are you getting? Hmm? Okay. So now, for this, so this whenever this for any two mutually exclusive events, they are not common. Okay. I mean, events no common elements. Then probability of A union B, okay, that will be that as there is no common element. So this we can define this is probability of A plus probability of A. Either A will be happening or B will be happening. So this probability of A union B, right? And then we will be defining this by this probability of A plus probability of B. Otherwise, the common thing we have to subtract away. Okay, right. So as this definition is there, okay, A intersection B is null, then we are having this probability of A union B equal to this. Now let us take one example that how this is coming into picture whenever we are taking the we are finding the probability, okay, of one event, right? We'll be taking taking that definition into account that mutually, I mean, all elementary events are mutually exclusive. Okay. So in our coin flip example, suppose that each of the four elementary event has probability 1/4. Okay. So this coin flip experiment, we had the sample space HH, HT, TH, and TT. Okay. And each of the elementary event will be happening. We are defining the probability law here. We are defining the probability law that each of the elementary event will be happening as equally likely case. That is 1/4 will be the probability of each elementary event happening. Okay. That is we are defining. But maybe if you are observing that you are dealing with some biased coin, maybe you can define your probability law according to that way. Okay. So here we are defining that each elementary event will be having the probability 1/4, right? Now this thing, so this probability of getting at least one hit, right? Probability of getting at least one hit. So now this at least one hit condition. So whether this guy will be satisfying this at least one hit, HH, at least. So not exactly one hit. Okay, at least one hit. So this guy will be satisfying this, right? And then this guy, whether satisfying this or not, this is satisfying. So this will be there in that event space. TH is also satisfying, but not TT. Okay, right. So you can think of this probability of this event, this A. This event may be comprising of this elementary event E1 union elementary event E2 union elementary event E3. Okay. Here, if I name accordingly, and then by that definition, that each elementary event is mutually exclusive, then we can find out the probability of this event A, which is at least one head out of this two simultaneous coin flip experiment. Okay. We can get this is probability of HH, that is probability of small e1 plus probability of small e2 plus probability of small e3. Okay. And then it is coming up as 3/4. Okay. So now in general, what we can say for this event A, okay, for the elementary events, so this probability of this event A, what we have already known that event A will be comprising of the elementary events. That is the first fundamental idea. We have to look to this sample space, we have to scrutinize the sample space, and then we have to collect which are the elementary events which are satisfying the condition of this event. Then that event space is created. Okay. Now this probability of A comprising of this elementary event, and elementary events are mutually exclusive. So we can write that the probability of this A is probability of this elementary event small s. Okay. So each of these is small s. We can say small s belongs to capital S. Okay. So this is one small s. This is one small s. Okay. So probability of this elementary event. Okay. We are summing up which elementary event, that elementary event which is belonging to this event space, okay, or the elementary event which is comprising this elementary or which is making this event A. Okay, not all the events, all the elementary events. The elementary events which are making this event A, the elementary events probability. So like the way we have done it here. Okay, all the elementary events. So this is transformed into a formula like this. So in general, whatever elementary events that will be making this A, if I sum up the probability of each individual elementary event, will be getting the probability of this event A. Okay, right. So this is the way we have to think. First, we had the sample space. Then the sample space, the elementary events, the outcomes are called the elementary events. Those elementary events, and we have to first come up with the objective that what are the events we are looking for. Then we are noting down those events, and then those events comprising of which elementary events that we have to find, and then probability of that event A we can find out by summing up all the probability of all those elementary events which are making that event. Okay. So this so far we have got this knowledge, right? So today up to this, and next day, next day we'll be having some idea about this expectation of a random variable, and then we'll be coming back to this. The last 10 minutes or so, we'll be coming back to this hiring assistant problem to analyze. Okay. Let's see what happens in the next class. Any question you can ask.